All right, guys, let's continue our discussion about catalytic strategies used by enzymes to carry out this phenomenal acceleration of chemical reactions. Um, so we talked about acid-base catalysis. We talked about covalent catalysis, and we talked about metal ion catalysis, which, as I pointed out last time, we can kind of group with electrostatic catalysis. Metal ions do more than just electrostatic catalysis, but they also do electrostatic catalysis. So I kind of group those together, but they're different things, right? Okay. So let's move to our next category: proximity and orientation, and then transition state stabilization. Right. I'll come back to a definition of that for you guys in a second. So let's talk about this idea of proximity and orientation. If we know that enzymes can enhance catalysis by doing acid-base chemistry and covalent catalysis, they use metal ions for various things, including doing electrostatic catalysis, or they can use their side chains. What does proximity and orientation have to do with catalysis? All right. Well, think about it this way. Most chemical reactions, all right, require the orbitals of the reacting molecules to behave in a particular way, to either come together or come apart in a particular way. In the case of bimolecular reactions, you've got to have multiple things interact with each other to get that chemistry to happen. And in free solution, that is, of course, as we've talked about thinking about protein folding, in free solution, that is going to be an entropically expensive thing to do. These individual molecules, say my square molecule or my square molecule, my round molecule, have their own intrinsic degrees of rotational freedom, vibrational freedom, translational freedom. They're hydrated, all that good stuff out in free solution. And in order to get these guys to react, we got to get rid of most of that, right? We've got to get these guys very close together, hold them there for some period of time, and therefore get them to form a bonding orbital. And that is going to be an entropically expensive thing to do, right? So one of the really important things that enzymes do, especially for biomolecular reactions, is to use their binding energy to pay some of that price, that entropic penalty for getting these molecules together on the surface of the enzyme. Now, there's another way you can think about this. The enzyme is essentially using that binding energy to create a situation of very high local concentration, right, between these things that need to react in the active site of the enzyme, right? So we talked about local concentration with respect to the way in which, or the reason that the weak interactions in a protein can be so much more stable than the free solution interaction energies would predict, because those local concentrations, because they're linked into a polymer, pays some of that entropic price of getting them close together. And that local concentration can be much higher than 55 molar water. This is sort of the same basic idea. The local concentration here for these interacting groups can be significantly higher, right, than you would predict. I'm having trouble with my presentation. Just from, or it can be significantly higher than the concentration of water. This local concentration, right, can be much, much greater than, say, the 55 molar concentration, which is the max you could ever hope to get, because that's the concentration of water, right? And you're never going to even get close to that, right? So the concentration of a solute in water is never going to get probably even very close to what water can be. But the local concentrations can be potentially an order of magnitude. There's some debate about this, at least an order of magnitude, maybe more than the concentration of water in free solution. So the local concentration of these reacting groups can be massively higher than they would be in free solution, right? So this is a powerful way in which you can increase the reactivity of a couple of molecules by bringing them together using binding energy to pay that entropic cost. Another important thing these binding interactions can do is they can strip water off of things that are hydrated on the active side of the enzyme, because you got to get the water molecules in many cases out of the way. And that's sort of all part and parcel of this creating this high local concentration of reacting groups. But there's another important thing this binding interaction does. It gets things positioned the right way. Remember, to get chemistry to happen, you've got to get these molecular orbitals to change around, right? And in the case of, say, for example, a classic SN2 type reaction. We have a tetrahedral carbon bonded to some element X and sort of classical sp3 sort of bonding interaction. You have a nucleophile that you want to displace X for in a classic backside SN2 type reaction. That nucleophile has to come in on the backside of that tetrahedral carbon and line up when this transition state happens, where you then shift the hybridization from sp3 to sp2p, right? So that the incoming nucleophile's orbitals overlap with that transition state p-like orbital on the carbon to then get the nucleophile to then displace the leaving group here, right? For that to work, the incoming orbital of our nucleophile here and this nascent, sort of in the transition state p orbital for the carbon have to be aligned. There's a limited angular distribution that allows this to happen. It's relatively tight. You can't come in orthogonal from the side, something like this. It's got to be in a fairly narrow angle. In free solution, you can imagine these things have to bounce into each other a whole bunch before you finally get that right. The active site of an enzyme, the rest of the things that the enzyme binding site is designed to orient these guys so this happens they settle down in the site and they're just lined up and ready to go, right? So that orientational, sometimes known as orbital steering, again, there's debate about exactly how much this contributes, but it's pretty clear that this does contribute a significant amount to how many types of chemistry happen in the active sites of enzymes, right? So then this, of course, lets things happen. Okay, now what about this last idea, transition state stabilization? To a real extent, everything we've talked about, acid-base chemistry, acid-base catalysis, covalent catalysis, electrostatics, this proximity and orientation idea that we're talking about right now, these things all go into recognizing, or they can all be described as recognizing key features of the transition state of these molecules and stabilizing that transition state. So they all sort of fit into this large category. In fact, some people would argue the simplest definition of what an enzyme does is use its binding energy to stabilize the transition states of key enzymatic reaction. That's the first order definition of what an enzyme is really doing. And all the way, we've seen some detailed ways in which that actually happens. But there's a whole set of additional ways that enzymes can do this that don't really fall cleanly into the categories we've talked about up to this point, and sort of are grouped loosely into this sort of larger basket of transition state stabilization. And another way to think about that is if you imagine, here's sort of an enzyme and substrate, right? And here's the enzyme substrate complex. The extent to which the enzyme binds and stabilizes the enzyme substrate complex is essentially that free energy difference right there, right? Okay, because we're going to bind things, that's worth some stabilizing free energy. But look at this. Look at how much bigger the free energy difference is for binding, right, of the transition state between the enzyme and the substrate, right? This is a much bigger difference in free energy. So another way to interpret that then is that the enzyme, in a general sense, is stabilizing the transition state, or it's binding the transition state much more tightly than it binds the ground state or the substrate over here, right? Okay, and there are all kinds of ways in which this can happen. Just as an example of, and again, everything I've described in the previous video and this one can fall into this larger basket of specifically recognizing and stabilizing the transition state. But there's some ways in which this can happen that don't have to do with pushing protons around or doing covalent chemistry or electrostatics, right? So here's an example. There's an enzyme known as proline racemase that can take L-proline, right, here, and convert it to D-proline, or vice versa. Essentially, it takes either an enantiomer, and then it basically, if you feed it a pure enantiomer, it'll allow, you get a racemic mix, right? But the way in which this happens, the only way in which this happens, this enzyme, is that the proton on the alpha carbon here has to be removed to create this sort of planar carbanion-like transition state, right? So you pop that proton off, you leave the electrons behind, you get this carbanion-like state, and the ring here is more or less planar. The formation of that carbanion forces it to be planar, right? And then of course you put the proton back on in the opposite face, right? And now you flip the stereochemistry. Here's something really interesting. People recognizing this, right, the sort of geometric features of this structure, wondered what would happen if they gave this enzyme a molecule that kind of just looked like it, right? Right. Unlike proline, right, D or L proline, which are that pyrrolidine ring is not planar. What if they gave it something that was planar? For example, this molecule here, this pyrrole 2 carboxylate, right? You'll notice because of the conjugation around this pyrrole ring, this is now a planar ring. There's one proton here, and there's a carboxylate hanging off. So the shape of this is very similar to the transition state. This molecule, this pyrroline carboxylate, binds to proline racemase 200 times more tightly than does proline alone, right? So that's sort of an example of this idea that the enzyme, even though, yeah, it binds its substrate because it wants to do chemistry, what it's really designed to do really well in terms of binding is recognize features of that transition state and stabilize that, because that's the name of the game, is pulling down the energetic height of that transition state barrier to get the reaction to get to equilibrium faster. Okay, now to see how this all sort of plays out, next video, we're going to see an example where these things are put together in sort of a fine-tuned dance to make a chemical reaction go very, very fast.